So my name is Stylianos, Chatzidakis. That's a long one, and usually I give extra credit to my students if they can pronounce my last name. I'm a professor, assistant professor with the School of Nuclear Engineering, and I'm working with Weatherman and Wanju Huang on a slightly different challenge than what we've seen before. Still, we try to see how we can leverage XR, but for an environment that actually has physics in it. So we're going to see how that would work when you have radiation and you have certain challenges there, and you also have regulations and you have radiation dose, and you see, hey, can I use XR to help me with that stuff? So this is a joint project between nuclear pharmacy and nuclear engineering, and we have very similar challenges. And again, we're very grateful to Envision and the Innovation Hub that kind of gives us this opportunity to leverage some of the XR technology. So I'll just go over some of the challenges and some of the ways we're exploring how to introduce XR options in some sort of physics-heavy and challenging environments. And I think we're going to have pretty good results. We're still early in the process. Another thing I want to mention is that I'll talk a little bit about nuclear pharmacy. Kara, she couldn't make it today, so I'll not try to do her job for her because she can do it much better than I am. So I might say a few things wrong. But I'll start that Karas is leading the nuclear pharmacy program here at Purdue, and it's one of the two labs in the US with a hands-on lab component. So that's very, very unique. It's really not easy to set up a lab like that. You have radiation, you have liquid radiation sources, there can be contamination issues, there can be radiation dose on the extremities of the students. You have to have a radiation safety officer approve your program. A lot of unique challenges, and Kara is doing great work in leading that stuff. I'm on the reactor side, and it's very similar to what Kara is doing. So some of the challenges, really unique challenges, is that once you start working with radiation, of course you cannot have your students or the technical professionals that come here to get trained to stay there and train as many times as they want, right? You only have some certain amount of time before you start going to the radiation limit. And if you go above that, actually, even if you go 10% the radiation limit, you have the radiation safety officer calling you and telling you why this happened. Then you have to fill like 10 paperwork, and they get upset. So you definitely don't want to optimize the training on, hands-on. It's really hard. There are contamination issues. You may have to shut down your lab for 6 months if there's a contamination. Radiation safety, there's cost. Time is a big issue. You can only train once. If you need to re-qualify, if you need to retrain, that's getting problematic there. The other thing is that how can you prove that someone is trained in the right way, right? So some of these students will become professionals, will go to the pharmaceutical industry, or we have technical staff from the pharmaceutical industry coming here to get trained. Well, how do you prove that they did everything right, that they know where the source is, how to detect, how to localize the source, and minimize radiation dose at the same time? So FDA, NRC, they want to see proof of that. So this is where XR comes in. So here's just a quick video of a Geiger counter. That's a pretty significant radiation source there. And you don't know that unless you actually scan and use the Geiger counter. So it's very easy for someone to start putting their hands in there to grab the source, and then their ring dosimeter will just go red, and you have no idea that. That happened until after a week that the dosimeter was sent for measurement. So Kara started this before I joined Purdue, so she's already done a bit of progress. Let's see, how do I start that? Okay. Folks, any help to George? Can you start the video? Yeah, okay. So we said, hey, can we use XR to kind of accelerate use of Geiger counters and radiation sensors, and how you could go about doing a contamination survey? So that was one of the first efforts that Kara did with Envision to make sure that the students can know how to use Geiger counters and how they can do a survey before they actually go in the lab. That started back in 2016 with an innovation grant. Now, the other part was that, okay, you know how to use the Geiger counter, you still don't see the source. Is there a way we can actually visualize the source? We can visualize radiation. We don't have senses for radiation. And then we see here George demonstrating XR with visualization of radiation. And you see the source, the container with the source, and the gamma rays emitted in a cone-shaped field of view. And one thing that happens is that, you know, students will just go and grab the source from above, or they will try to grab something else and will just have their hand go above the source. You couldn't see that before. So you had to go to the lab, and then how you know that you're getting more dose is that, again, you look at the dosimeter, and then you have to go back and optimize. But right now you can use the XR and visualize the radiation, and you know, okay, this is the field of view, I need to avoid that, and I can go on the side, or I can shield it, and then that would make radiation handling much easier. Now here's the part where physics come into play, right? We don't have data to feed in the XR, so the XR platform has to generate the data. So we need to combine the XR environment with some physics running in the background. And physics there, that's a challenge. What physics do you add? You can have low fidelity physics that run really fast. It's easy to code, but they're not very accurate. Or you can do some higher differential equations, higher order differential equations that will take a lot of time to run. So how do you solve this challenge? For example, here you see the gamma rays just going straight up, which is quite realistic, but not exactly 100% realistic. So there's no scattering, some very simplified physics, but still might be good solution for this environment. I think that's another version of radiation visualization. I think here the next iteration was that you can use this, and then the EXR platform will tell you how much dose the user got, and it will give you a report and say, hey, this is how many times the wrong action happened. So then Kara can go back and talk with the student to optimize the actions there. And you get, you can get a graph that shows the movement and the tracking of the hands and everything, which can be very, very useful. And it was really hard to do before. If you have 10 students in the radiation lab, you cannot micromanage all of them, right? Some of them will spill the source, would not manage the source really well. There's no way you know about that. But here's there's proof and also improvement over time. 2017, Kara got another grant to develop an XR environment for a technetium generator. That's something that's used for radio diagnostics. Same idea as before. How can you make sure you are operating the equipment properly? One big challenge is with this equipment is very expensive. It's same for my lab. We have some very high, very expensive detectors, very sensitive. There are many times that the students, they just accidentally destroy the detector because the voltage was higher than what it was supposed to be. That's a great example of how you can learn to operate the equipment before you go in the lab. So when you go there, you already know how it's working. So very good detail here. I was very impressive. Again, there are physics involved, which makes it quite challenging from the XR side of things. And what happens here is that there's a whole procedure that someone has to follow, and you follow the procedure, and the XR platform will record, it will log the steps, and then you can see how many steps were followed, how many steps were missed. And then I think at the end, you get a score if you've done everything right. You get the actual dose, 1 millirem per hour. Recorded was 0.99, was great. What was the distance that you followed? I think same thing here, right, with the XR. So that's a Geiger counter that we use in the lab to identify radiation. And usually it would take a whole semester for students to learn how to use that and how to protect themselves. We've been seeing good acceleration in learning for the students. We're still early, but it's really showing promise. And that's another report that has more details. And you can actually show that to an FDA inspector and say, hey, look, I trained my students, and this is proof that they did everything right, and now they can get the certificate and go work in the industry. Big thing with the industry is that they're reaching out to us and say, hey, we need to train, for 1 year a technical technician to handle these materials. Can we use that to train them in 3 months instead? That will save millions and millions of dollars. So they're reaching out to us for that. So I think this effort will definitely pay off in the future, big time. Of course, COVID, that was a time everybody wants to forget, but that was also something that Kara implemented during COVID, and it worked pretty well. And recently, this is the effort where I'm working with Kara. We got another innovation hub to further improve this effort and add the nuclear engineering part, which is the reactor, and I'll go in the next slide. So I think that's the latest version. It's much more greater detail. And again, doing a contamination survey with a Geiger counter, plus the collaborative environment with the students. Okay, so just talk a little bit about the reactor. So this is our reactor. We do have a reactor on campus.
Is it the one underground physicists?
Yeah, definitely. You cannot get access to that unless you talk to me. It's in the basement of EE. So there's a reactor on campus, and it's pretty amazing facility. Here's the core. You can see the core. So that's the reactor core, the console, and then we have the instrumentation and control. And it's you can actually see the core. It's a very unique reactor. It's one of the few in the nation. It's an open pool. So it's a pool filled with water, and you can come and see the core. And this is how it looks when the reactor is operating. And there's this nice blue light. That's not Photoshop. This is actually Cherenkov radiation that's emitted when electrons are going faster than the speed of light in water. So we do a lot of things with our students. You can come and see the reactor. Just send us an email, and we can schedule a reactor tour for you. So we're using the reactor with undergraduate nuclear engineering students training, graduate students. We have summer camps for high schoolers. A lot of good things. The big problem, of course, it's a reactor. Right? You cannot turn it on. You cannot turn it off easily. So, right, there's a whole preparation that has to go with that. You have the reactor supervisor. You need reactor operators. So again, this is where XR can come in and help us kind of speed things up a little bit, and even do more, right? Because even when you train in the reactor to operate the reactor, you cannot actually do an accident, right? You wouldn't want to do that. So it's kind of hard to get trained for emergencies and stuff like that. So what we did with Envision is that we mirrored the operator console on the virtual lab. And not only that, but we added additional capability, can provide more graphs, more data, more diagnostics. You can do a 3D tour of the reactor. So someone can use that, spend as much time as you want. You don't have to wait for the reactor supervisor to turn on the reactor for you, which only can do a few times per year. But you can do that, at your house and train 2-3 hours per day, and then you come there and you take the exam and you have your license. Of course, you still have to train on the actual reactor, but it's much less time-consuming, much less risky. Also, with what I was saying earlier, we have some very expensive neutron detector equipment. We spend a lot of time to teach students how to train and how to use this equipment. Of course, sometimes the students might accidentally turn on the high voltage too high, and then the equipment will burn. How can we avoid that? Again, virtual lab, XR, and moving that to XR, that has helped a lot. We deployed that last semester. Students loved it. Physics is what really it's taken a lot of time because the physics can be complicated. The visual artists, they have to understand the physics, and we have to benchmark the physics, right? We want to make it as realistic as possible. There's no point in having false physics there. So I don't know, Joseph, we can do a demo, or if we just skip that. I don't know how. We can do it. Yeah, okay. And I think that's the last. I will have one more slide when we're done. Yeah, so if you go, yeah, George, if you go back, let's go back first. And if you go back, if you click where it says reactor, yeah, and we can use the right click. Yeah, you can, so you can see the reactor right now. You see that's the actual very realistic reactor room. That's how it looks like. And you can see all the components, you can see the hubs, you can, we have quizzes there for safety, we have quizzes for the reactor, and students can use that. And then if you zoom in into the console, you can see the actual console of how the reactor is and what an operator sees. I think you have to click them, yeah. And you can start the reactor shut down or already at power, so you don't have to wait 2 hours until it goes at power. And you can do a scrum, you can shut down the reactor and all kinds of other things. And the second one was the neutron detection lab. So Julian, if you could give us a quick demo. Okay. So
I'm done. There we go. Safety quiz.
Yeah, that's another thing. For everyone to use radiation, you have to go through radiation training, you have to do quizzes, you have to prove that you know what you're doing. That's about a month of work even before that. And that the yellow bar, there's the radiation source, the electronics, there's the oscilloscope, and everything has its physics in the background. So that took us months to just fine tune and benchmark, but it's very realistic. If you come to the lab and do that, you see here, you increase the high voltage. That's how the students do that. So you have to put the proper voltage. If you don't, there's an alarm, there's a red flag. Maybe, Julian, you can.
I'm just going to do the oscilloscope just to show that the oscilloscope is functional.
Yeah. Yeah, you get the pulses, and then you can send the pulses to the monitor, and you can see the spectrum. Yeah, so that's even you can see the noise there. So there's even a little bit of noise to make it realistic. You can change the resolution of the detector, things you cannot do in an actual lab. In an actual lab, you only have one detector with a certain resolution. You cannot change the resolution to see how things are changing. So that has been a very useful tool for us, and we want to deploy it more and more and more. Okay, and going back. Yeah, so that's this is the reactor now, the XR version, where you can actually, the idea is that you can zoom in and actually zoom in the reactor core, and you can change the control rods, you can start moving up and down, and you can see the hotspots, you can see the neutron flags, the heat map. You can do things that it's impossible to do with the actual reactor. Plus, there's the Geiger counter again that can tell you where the radiation is high, where it's low, so you can prepare yourself before you go in the reactor. Okay, so some really quick key takeaways. This XR experience has been very helpful. It can definitely accelerate the way students understand the concepts, not only seeing the equations, but actually feeling and interacting with the concepts. Definitely very helpful in reducing radiation dose, preparing the students to come ready to train and use the equipment, saves a lot of time. And I expect to use that more and more and more as we're seeing higher enrollment. Like, for example, last year I had 40 students in this radiation lab. This year I had 70, we expect 100 next time. So it's getting really problematic to get more detectors, more equipment, more space where you can use that to save you a lot of effort. Yep. George? Okay. Yeah, and of course, acknowledgement the team, our undergrads are doing a great job. Envision has been very instrumental in moving this forward, and of course, the Innovation Hub for providing funding and support. Any questions?
Please. So I noticed you use the Unity game engine for at least some of this, so.
For everything.
Yeah, how was your experience with that? What made you decide to use that? And how did, who was involved with actually coding up the environments?
Yeah, so how it works, and so how it works is that Envision will take care of the graphics. The platform will provide the physics in a sort of MATLAB code or C++ code, and then they will also include that integrate that into the platform. But they are the leaders there, they handle the Unity, because I have no idea.
Unity is very easy to deploy to web, VR, desktop. To build it once, you can deploy anywhere you want. So that's why we use Unity.
Thanks.
In Unity, what packages do you guys tend to use in your different applications?
I can't speak for the radiation or the nuclear reactor simulation. I think we use a MATLAB runtime so that the nuclear department can provide us with MATLAB code that runs and interfaces with Unity. On the second virtual lab that you saw toward the end of the slide, I think the only package that we had used was one called OB-Rope for the cable physics. Everything else was built inside the center. Either inside the center or the equipment simulation code was provided to us by the department.
I think we have time for maybe one more question.
Yes.
So here we have the simulation for one team member, yes? Is there a chance that we can have more different team members together in the same environment? Is that something available?
Yes, that's the goal of the last slide of the last XR demo, is to actually have a collaborative environment in the reactor room. Everybody collaborating, looking for radiation, for sign signatures of radiation, and I think that's the goal of this grant, to make it collaborative.
That reactor clip was taken inside the same platform that we had shown earlier in the day with multiple people co-located in the same space. I just didn't have anybody else connected to that session, but we very easily could have just connected to it just like any other virtual classroom space that we have.
Thank you.
Thank you.